In the previous video, we kind of explored a pattern that was going to emerge whenever we took the derivative of a power function. And in fact, we do get a very simple thing called the power rule for taking a derivative. And it says this, it says that if n is a rational number, then f of x equals x to the n. So here's our power function. X is being raised to some power, and in fact, the power just has to be a rational number. So n can be negative, n can be a fraction, it can be an integer value. We actually get a lot of power out of the fact that n just has to be a rational number here, that it doesn't have to just be an integer. So if I have anything that I can write as x to some power n, then this function is differentiable, meaning I can take its derivative, and the derivative with respect to x of x to the n. So this notation right here means I'm going to take the derivative of x to the n. What it equals is I can take the power, in this case n, and bring it in front as the new coefficient. And we kind of saw why that ends up being the case in the previous video. And then I need to reduce the power n by 1. So it's nx to the n minus 1. And in the previous video, we talked about why that power gets reduced by 1 as well. The other thing that I can say is that the derivative of x to the n, just kind of using that notation, Newton notation, but it comes out to be the same idea. So here's some examples, and you'll see very quickly that you're going to be kind of flying around taking derivatives now if you understand how this power rule works. So if I have the function x to the fourth, f of x equals x to the fourth, without having to apply that limit definition, which can sometimes be gross, you get to jump right in and say f prime of x is equal to, well, the power 4 becomes the coefficient, and then it gets reduced by 1. F prime of x is 4x cubed. You're done. No limit statement, no nasty algebra trying to figure out what x plus h to the fourth is. There's your rule, and that's how easy it's going to be moving forward, at least for these particular functions. If I have g of x equals x to the 10th, there's a function you really don't want to do the limit definition with. You don't want to know what x plus h raised to the 10th power looks like. Fortunately, this power rule allows you in just a matter of seconds to say, okay, bring the 10 in front and then reduce it by 1. G prime of x is 10x to the 9th, and you're done. That's it. A really big one, and sometimes one that you can kind of forget about, if I just have x, that's a power function. It's x to the 1 power. So h prime of x says take the 1, bring it out in front, and then reduce the power by 1. So what I get is 1x to the 0. Well, x to the 0 is just 1. So h prime of x is 1. And that also makes sense if we understand that h of x equals x. That's a linear parent function. Its rate of change, or its slope, is equal to 1. And that's what this is saying here. But understand that the derivative of x is always just going to be 1. That's something that comes up a lot and can sometimes be a little bit easy to lose as part of your work when you're taking more complex derivatives. So don't lose sight of the fact that this is going to be true. I also mentioned earlier, this works if n is a rational number. So let's say that we have j of x equals x to the minus 3 power. I can use this rule to take its derivative. J prime of x, make sure you follow the rule which says to bring the power in front as a coefficient. So negative 3, x, and then the rule says to reduce the power by 1. Well, negative 3 minus 1 is negative 4. So just make sure you're kind of sound on your number line there. When you take a negative number and subtract 1, it can be very easy to say that's minus 2. Make sure you do, in fact, subtract 1 from the negative value. And for what it's worth, I could also rewrite that j prime of x as negative 3. I can take a negative exponent and rewrite it into the denominator of the fraction. So it's pretty easy to take a derivative of this function j of x. In fact, in the next video, what we're going to focus on is a function that maybe doesn't look like this, but a very easy rewrite can turn it into a power function, and then we can apply this power rule to take its derivative.